This is lecture number 21 of the course AU 203 Statistics and Quality Control. In this lecture, we will talk about exponential distribution, and obviously we will look into the parameters related with exponential distribution and its mean and variance. There is an extension of the exponential distribution, which is two-parameter exponential distribution. And then we will look into an important property related to exponential distribution called Memoryless Property. So there is a mathematical function. If you substitute some continuous random variable x, you are going to get its corresponding probability. So this function is represented by some exponential function, negative exponential function, actually e to the power minus x over theta, and 1 upon theta, where theta is its parameter. So any value of x greater positive value bring corresponding probability. So if we look at the plot, when x is come out to be 0, then e to the power 0 is 1, and 1 upon 1 into 1 upon theta would be 1 upon theta. So its corresponding value when x is 0 would be 1 upon theta. Then as x increases, the value of that function starts decreasing, and once x approaches to infinity, the value becoming small and small approach towards 0. So this is a typical behavior of this exponential distribution. Let's say if we change different parameters, let's say here in this plot, the value of theta, if it is taken as 0.5, then you have this such a steep curve. Then 1 upon 0.5 would be 2 would be the value when x is 0, and as x increases, the value of the function decreases sharply. So this would be a typical behavior. As parameter theta is increasing from 0.5 to 2, then 1 upon 2 would be 0.5, so 0.5 would be the value of f of x, and then starts decreasing, and the dashed line is representing, the color dashed line is representing this behavior. If we have theta a big value, let's say theta is 10, then it would be 1 upon 10 would be approach towards 0.1. Then the value of that x is with 1 upon theta. So it's almost a very small change in that value, but as x approaches to infinity or a very large value, all parameters would end up into the same limiting value of approaching 0. So this would be a typical behavior of this exponential function. So here, if there is a single parameter involved, theta, so is a single parameter distribution with this, and since we have seen that it is rightly skewed, it means once on the right hand side the value increases, its corresponding probability or the value of that function is decreasing sharply. So it is a right skewed distribution. Okay, let's say if we have always, whenever a PDF of any distribution is given, the good thing is to start whether it is a legal PDF or not. So if it is a valid PDF, as we know that for any value of positive value of x, that would function would result into a positive value. That is the first condition. And the second condition is if you integrate from the limits minus infinity to plus infinity, you must end up with 1. So let's check out if because it's satisfying always the first condition for whatever the value of theta is, just integrate this function. So 1 upon theta is a constant, so you can take out as out of an integral, and e to the power x is integral is e to the power x. And since it's not x, it is x upon minus x upon theta, so its derivative would be minus 1 upon theta in the denominator, and substituting the limits up, as you know, since minus infinity is not possible because our limiting value for x is either equal to 0 or greater than 0, so the lower limit is replaced with 0. And then you just substitute the value, then you end up with 1. So it means this is a valid PDF because it is satisfying the general condition for any PDF to occur. So let's say this exponential distribution, if we have to calculate the mean value, so mean value is just the expected value. So what you need is to integrate this function. I'm not integrating it, but you integrate this function theta times 1 upon theta, and theta in theta cancels out, and you integrate it between the legal limits. You will end up with a parameter called you will end up with a value called mean value. And here the mean value is actually the same thing as the parameter of the distribution. So whatever the theta is actually the mean value of the parameter. So we have seen the distribution looks like for different values of theta, and once mean is a small value, then the most of the probability would be close to 0. That is what we have seen is when x is very large, then you see whatever the value is, you are all approaching towards the 0 mark line. And so the variance is exactly the same definition. If we calculate the variance of x, where x is a continuous random variable, we are not going into deriving this expression, but just writing down, and you can do it at your home, deriving this expression for variance, which is actually the 1 upon the square of the parameter. So here variance is actually, you can think of it is actually like mean squared. So and if we have to calculate the cumulative distribution function CDF of that, so we have to integrate from 0 to some value of x, so that area under the curve up to the threshold value of x is less than x. That would give you the cumulative density function. And since x is in the limits of our integral, that's why we are dealing with, instead of writing down x upon theta, we can write u upon theta, because here u comes out as a dummy variable. So just substitute f of u means 1 upon theta e to the power minus u upon theta. Substitute here and integrate. You are going to get this function. And so here you see 1 minus e to the power minus x upon theta gives you the cumulative value at a given random variable. And we can learn quite easily, if you differentiate this expression, the derivative of 1 would be 0, and minus cancels out, so you are going to get the same function. So in general, for any CDF, if you differentiate, you are going to get its PDF. Or if you have any PDF, if you integrate, then you are going to get the corresponding CDF. So this relationship to be applicable to any PDF. Since the PDF of exponential distribution is quite simple, and the differentiation and integration is simple, so you can check with this distribution. But for if you look at the PDF of a normal distribution, this differentiation and integration could be more complicated. Okay, now let's see how we can solve problems related with exponential distribution. Here you have a distribution with a mean value of 6 megapascal given for a model for the distribution of stress range in a certain bridge connection. So what is the probability that the stretch range is at most 10 megapascal? So its mean value is 6, and we have to see whether its value is at most 6. So first thing is always define a random variable here. X is a continuous random variable, which is actually representing the stress in a certain bridge connection. So the information that has been given here is the mean value, which is actually the expected value. So the parameter value of theta is given, which is 6 megapascals, because that is given. So the first thing is, as we know, probability when x is less than equal to x would be some CDF of that variable x would be 1 minus e to the power minus x over theta. That is what we already have derived. So the first part can be easily calculated because your x could be maximum at most 10, so it would always be either equal to 10 or less than 10. So your random variable would have a value either is less than 10 or equal to 10. So that can be easily worked out just by substituting into a CDF. We can calculate the corresponding probability. Let's say in the second part, what is the probability? The stress range is in the limit from 5 to 10 megapascals. Its average value is 6, and they are interested in a value from 5 to 10. So we need to integrate actually between 10 and 5 for that CDF value. So f of 10 we can easily work out just substituting x value 10 and theta is 6. And since the x here is 5 and simplify it, so the area under the curve in that limit between 5 and 10 would be 0.246. So I have used this. You can directly use the PDF to calculate the same thing as well. So there are different ways of finding out. In exponential distribution, the CDF is simple to calculate, which is almost 1 minus somewhat closer to the negative exponential function. The same thing we can do it in the mini tab. We will see if you go onto the mini tab, you can easily plot these values, and you can do it. In the end, I will show you all this. Okay, there is a 2-parameter exponential distribution. So as you know, theta is an average value which is representing different shapes. So different values of theta is representing different shapes. And if there is a threshold parameter, which is actually a location parameter. So for example, if we have this distribution and gamma is that value which is shifted to the right, so that is actually called as gamma is actually called as threshold parameter. And if the value of the gamma is positive, obviously we are shifting it to the right, and if it is negative, then it is shifting it to the left. So it is just a location parameter, whereas theta is a shape or scale parameter, because different values of theta would result into a different shape of the probability density function. For example, when you are interested in studying the failure of a system with threshold parameter 5, it means actually the failure starts to occur only after 5 hours of an operation and cannot occur before. So because let's say the function is representing probability of failure. So let's say if your gamma is 5, it means there is no failure associated up to this threshold number 5. Let's say it could be a 5 hours of an operation, and after 5, then as the time progresses, the rate of failure is initially very high and then starts decreasing it. So this is the physical significance of the second parameter gamma. Most of the time this gamma is, once this gamma is 0, then it becomes a single parameter exponential distribution. Okay, at this point there is an important property of exponential distribution that is called as memoryless. So just consider a device that has lasted a length of time t. So x is a random variable, which is, let's say, think of a time to failure. So this is actually a time scale, and we already know that a particular device has already survived up to time t, small time t. And we are interested in calculating the probability that this device will survive for additional length of time a. So then the final time would be t plus a. So if this is your scenario, then the same thing can be written in the language of probability. And since we have some prior information already available for the probability that the device has already survived up to time t, so we need to represent it into the definition of conditional probability. So in the language of probability, this statement can be written as: we are interested in calculating the probability that x is a random variable which is representing the time to failure, which is a continuous random variable, and it would be survive t plus a value, and this such that, or given that the random variable is already greater than t, means it already passed the time t. So this is the same statement can be written in this mathematical form, and we know from the formula for conditional probability that this and this divided by the probability x greater than t. So it means probability x greater than t plus a and probability x greater than t divided by the probability x greater than t. Simple like that. Probability of a given that b has already occurred equal to probability of a and probability of b divided by probability of b, because whatever is here that goes into the denominator. So it is exactly the same definition of conditional probability. We have simply rewritten it in this form, and this is exactly representing the same fact that x is your random variable, which is actually in this case time to failure of a particular device, and we are interested in calculating the probability that a particular device will survive for time t plus a, such that it has already survived up to time t. Its probability would be equal to just as we have written in this using conditional probability. So now let's say we already have survived up to time t, so the random variable would always be greater than time t. So any value of x would come would be greater than t. So if you see, the common area between two would be anything which is t plus a. So the common area between when x is greater than t, it starts from t, and when x is greater than t plus 1, it starts from that place. So the common area would be something which is greater than t plus a. So that is the intersection part is in the numerator, and the denominator is exactly the same. And then the next step, we can say that x greater than t plus a means 1 minus x less than equal to t plus a. So just writing the complementary part of that probability, if probability x is greater than this, would be 1 minus probability x less than or equal to this. Okay, so in the numerator, as you see, it is exactly the same as the definition for CDFs. CDF always says your probability of x is less than equal to some critical value a or b or c, whatever. So here this critical value is t plus a. So 1 minus, and this thing can be written using the CDF where just substitute the value of x to be t plus a, and x greater than equal to t means 1 minus probability x less than equal to t. So probability x less than equal to t can be written with this expression for CDF. So the right hand side has been transformed into the CDF. Okay, so this thing as I know already for exponential distribution, if my x is t plus a, 1 minus and this f of x would be 1 minus e to the power minus x upon theta, and x here is t plus a. And similarly for f of t, so you substituted that. Okay, now we need to simplify this expression. 1 minus 1 would be cancels out, so minus and minus would be plus e to the power minus t upon theta plus a minus a upon theta, and denominator is also simplified e minus t upon theta. E minus t upon theta and t upon theta cancels out. So what we end up with, this conditional probability is interestingly is independent of time t. So it means it is memoryless, because our random variable is that x is a time to failure, and we are interested in calculating the probability that a device would survive time t plus e such that it has already survived up to time t would be equal to e to the power minus a over theta. So in this expression for probability, there is no variable involved like a variable like t. So this desired probability is independent of t. So the length of the time the device has already survived has nothing to do with calculating this conditional probability. So it just involved how much is the additional time that is actually involved. So it is just a feature of this particular distribution which result into this expression. It will not come into for every PDF. It will come into with this special exponential distribution where this conditional probability would be independent of time t, which is actually the time t is actually such a time where your device has already survived. So in calculating this probability, we don't need to know whether it has survived for a particular time or not. So this property is very useful because when you are predicting the remaining life of a component which is not depending on to its current age. So it means, for example, whenever a system experiences wear and tear, and we already know that due to the wear and tear, the likelihood of failure increases. But once you have repaired in such a position that it doesn't remember whether it has failed in some time in priori, then this distribution can be used to predict, because it does not remember whether it has failed in the past or not. So once you repair some device after failure and it is as good as new, then this thing could be used. But in reality, we already know after a maintenance or after repair, the product does not have the same probability of surviving. So in reality, it is different, but we can say it once you have such an assumption, then this distribution to be used. This distribution is very widely used in so many things. For example, if you look at the PDF of that distribution, just like in the beginning, then this PDF is, for example, when time is 0, the probability of failure is very high, and this happens for most of the electronic components. So you see, once you install a bulb and you just try to switch on and it fails one just to switch it on, so the probability of failure is very high. But once it has survived up to certain time, and then their probability of failure decreases. So this happens in most of the electronic product. They functions well for a long time once they have survived their initial time. So this behavior is the feature of this exponential distribution. That's why it is mostly used in predicting the time to failure for electronic components. So this exponential distribution is used to model the time between occurrence of successive events. So it is not just a failure, but such as customers arriving at a service facility. So the probability of finding out what is the probability that your next customer would be coming after 2 hours or 3 hours or something like that. Or for example, if you're on a telephone board, so number of calls you are going to receive. So occurrence of the next event or a successive event, if you need to calculate its probability, you can use this exponential distribution. And if you recall back, it is somewhat this exponential distribution is very much related to the Poisson process, because in Poisson process it is actually almost a reciprocal of this. So if you compare both Poisson distribution, which is actually for a discrete where your number of defects you are interested in, or average number of defects, here you are interested in average occurrence of an event. So it is just reciprocal of the Poisson distribution. In some cases, like when your failure rate is constant, so this exponential distribution is used to predict the probability whether the device is going to survive or not. So I have already mentioned, for example, in some cases like radioactive decay of a nucleus, so you need to know the time to decay. As you know, once you have at a small time, then their number of atoms are much bigger, and after some half-life the number of atoms becomes n by 2. So this is the negative exponential function in those applications where this negative exponential function is used, where we can use this exponential distribution to predict the probability. There is queuing theory I have already mentioned once you are interested in calculating the waiting time. For next customer or next service time, and you know how much is the average rate of occurrence of service time, and then what will be the probability that you're keeping view in average, what will be the probability that the next customer would come after that time. There is one more application which is actually called as Markov Chain, which is actually a stochastic model. So actually there are two things, and once you develop a model which predicts the future behavior, there is some models which are called deterministic model, which is somewhat based on differential equations or mathematical equations, where you can predict once you put certain values of x, you are going to get a particular value of y. But once your model is stochastic, so it means it is a probabilistic estimation. So in such cases, there are such models to be described as a sequence of possible events in which the probability of each event depends only on the initial state attained in the previous state. So once you're moving from one state to another state, and the time is continuous variable, and just like the same as a Poisson process, such process is actually known as a Markov process. Markov is just a name of a scientist, and such chain which actually describes a sequence of possible events in which the probability of each event depends on to the initial state. So this is a stochastic model, so you don't need to go into the detail, and you need to solve problems related with exponential distribution, and it is mathematically one of the simplest of all. So this is where I stop the lecture. Okay, so on mini tab, how you can use this, go to the graph and probability distribution plot and view probability, and we have to choose the distribution here. Let's say here it is an exponential distribution, so it gives you the scale parameter as well as the threshold parameter. So let's say for 6 megapascal was your average value or scale value theta, which is given here in this problem, and let's say I'm interested in calculating the value which is left tail, let's say less than equal to 10 megapascal. So if let's say this was the case, if you just click on, you will be able to calculate this 0.811 is actually the probability you have when your value of x is because threshold value is 0, so because there is no shift, and the scale parameter here is theta would be 6 megapascal, and up to less than or equal to 10, this would be the probability. And if we have to go to this probability distribution plot for shaded area between two middle value from, let's say, from 5 megapascals to 10 megapascals. So in that range, that would be the corresponding probability, which is 0.2457. I don't know, the value from 5 to 10 is 0.2457, so it is exactly the same. 0.24567 is the probability that your stress for a particular component lying in that range. So this is how you can use, and obviously you can calculate the probability directly from this on the instead of going into the here scale parameter, you need to calculate probability, let's say for 6 megapascal, and threshold value, your input value is, let's say, 10, not input column but actually your input value rather. Okay, so you don't need to write input column, but input constant. Input constant is 10, then you are going to get this value. So it is, you are getting this probability, corresponding probability. So once you are interested in the area under the curve, you need to calculate the cumulative value up to 10. So if I go on again doing it, this exponential distribution, and let's say this cumulative probability, okay, at this point now I'm going to get that number 0.811. So 0 to 10 would be 0.811. So when your random variable is less than some 10 value, then this would be your corresponding probability. So this is how one can use or you can compare different probabilities, let's say by varying the parameters. Let's say I select here exponential distribution, and let's say my threshold is 0, and I just got it to 0.5 and 2 and 8. Let's say 3 different values of the parameter, and I want it let's say on this overlaid on the same graph. Okay, so once I overlaid on the same graph, so you can see that these different values. So just like I just make its maximum value to that not maximum value is instead of just make it 1, let's say. Okay, even not 1, maybe 0.4. I just take it maximum value of 0.4, or let's say 0.4. I could see that okay, so now I can see that different values of x, when x is 0.5, the curve looks like this. Even I think this would be maximum value, just I take it just smaller than like maybe 0.1. Makes sense. Okay, just a 0.1. Okay, that's this you see. So all values when x increases going towards approaching 0, and this is when it is 0.5, this is when it is 2, and this is when it is 8. So this would be the typical behavior of this exponential distribution, and you can see in such plots. So okay, so